All right, we're covering a lot of sections here. That's okay. It's not going to take too long. So I'm going to give you two essential questions. The first one is, what is true about the side lengths and angle measures in isosceles and equilateral triangles? And the other one is, what are the triangle congruence theorems? Oh, we won't stop there. And how do you use them? To show triangles are congruent. Okay, so we're covering a couple of things. I'm going to start with 5.4, and that's about isosceles and equilateral triangles. And then 5.3, 5.5, and 5.6 is all the triangle congruence theorems. Okay. Let's start with 5.4. It's pretty darn simple. So 5.4, isosceles and equilateral triangles. So we have an isosceles triangle. And what you already know about an isosceles triangle is that there's going to be two legs on that triangle that are congruent. Okay, well, the base angles theorem then states that if two sides of a triangle are congruent, which means it's an isosceles triangle, then the angles opposite them are also congruent. Okay, so what we can conclude then is this. I have two congruent legs, so the angles opposite those legs, so this angle here and this angle here, are also going to be congruent. Okay, so this is where the base angles theorem, that's what it's telling you. Now the converse of the base angles theorem just means like go backwards now. So now you're told that the two base angles are congruent, so what can you conclude? Well, you should be able to conclude then, if the two base angles are congruent, then these two sides opposite those base angles are also going to be congruent, and therefore we know that this is an isosceles triangle. So that's what this says. If two angles of a triangle are congruent, then the sides opposite them are also congruent. So we can conclude now this, and that this is basically an isosceles triangle. And then all of this extends, what we just did, also extends to equilateral triangles. So an equilateral triangle basically means that all of the sides are congruent. Okay, and then we've got this corollary, so it's like an addition to the base angles theorem. It just kind of is an extension, I should say. So if a triangle is equilateral, then it's also equiangular. Right? So because we knew, okay, these two sides were congruent, so then the angles opposite them will be congruent. Well, now we got three sides congruent, so also this angle over here will be congruent. So we can conclude then that these three angles are congruent. So an equilateral triangle is also equiangular. And here we're given, and this is just the corollary to the converse of the base angles theorem. Okay, so it's just like a little extension of it applied to equilateral triangles. So here we're given all of the angles are congruent. So what can we conclude? Well, we can conclude then that all the sides opposite those angles, and this one, they're all going to be congruent. So again, I got an equiangular. They gave me an equiangular, and now I know that it's also equilateral. Okay, so let's do a couple of those examples. So start by finding the value of x here. Well, this is an equilateral triangle, so then I know that it's also, if all the sides are congruent, then that means that all the angles are also congruent. Okay, and so that tells me, well, basically 2x plus 2x plus 2x is equal to 180. So you can write it like this. Or that's the same thing as saying, there's 3 times 2 of those x's. Or, sorry, times 2. There's 3 of those 2x's. That's what I meant to say. Right? So that could just be 3 times 2x equals 180. That's the same thing. Either way, if you combine these, you're going to get 6x. And here, you're also going to get 6x. So you got 6x equals 180. Divide both sides by 6. X equals 30 degrees. Or just 30. It didn't ask me to find the measure of an angle, just asked me to find x. Okay, next one. We're going to use isosceles and equilateral triangles to find the values of x and y. Okay, so I know that this is an equilateral triangle. Great. Or sorry, an equiangular triangle. That's the correct language, which therefore means it's also equilateral. So this side and this side and this side are all congruent. I think I'm pretty much done. So that basically tells me that 4y has to equal 28. Oh, that's an angle. Never mind. So that's it. Okay, so we'll start with that one. So if 4y equals 28, divide both sides by 4, then I know that y is equal to 7. Okay. Now the other thing I know here, let's see. So this side here is 28, and so is this side. So now I've got this isosceles triangle. So this, let's see, let's maybe use pink. This triangle right here is isosceles. Once again, every single side here was going to be 28. Well, so is that side. We don't know what that side is. But so these two sides are 28. So I know it's isosceles. So I know that all my base angles are going to be the same. So my base angles here, maybe if I flipped it upside down, right? The angle opposite of this side is that 2x. And I don't know what that one is. I'm going to put 2 arcs there because I don't know if it's the same as that one. And then the angle opposite this side is going to be the same, whatever that is. Okay, so we got to figure out what that is. Well, let me turn this back around. If all 3 angles are the same in this triangle, whatever that is, right? That's x plus x plus x, so that's 3x equals 180. Maybe I shouldn't use x. I should use something else. How about z? So I'll call these angles z. Okay, so this angle, and that angle all together equal 180, or in other words, z is equal to 60 degrees. So each of these angles equals 60 degrees. Well, I'm only finding one of them for now. Now, I know that this angle here, and how about I'll call this angle W. Angle W, those two add up to what? Well, they form a linear pair, so they add up to 180. So I can say that W plus that 60 degrees equals 180, or W equals 120. Okay, so this is going to be 120 degrees. Well, 120 degrees plus these two congruent angles is going to have to equal another 180 degrees, right? So 120 degrees plus, well, this angle is called 2x, and this angle is called 2x as well, right? That's going to equal 180 degrees. All right, so simplifying that, I get 120 plus 4x equals 180. I'm running out of room because I didn't think ahead here. I'm going to subtract 120 from both sides. Get it a little bit smaller here. Okay, so coming from here, I'm going to say, well, then I've got 4x equals 60. This is something completely different. Let's see if I can kind of make that its own thing. And then I'll divide both sides by 4. I get x equals 15. So x is equal to 15 and y is equal to 7. We answered everything. All right, let's see what we got here. So in the diagram, segment PT is congruent to segment ST, and segment PQ is congruent to segment SR. Explain how to prove that triangle PQT, I find it helps with highlighting, seeing different colors, and triangle SRT explain how to prove that those are congruent. Okay, so, well, first of all, let me flip this upside down. One thing I know, that this big triangle, triangle PTS, this one right here is an isosceles triangle because those two legs are congruent. Therefore, base angles are going to be congruent. And that's as far as we can go until you get the rest of the information from this lesson. So we will come back and revisit this problem. So now what we're going to do, if you flip the page, we're going to work on this triangle congruence theorems foldable. So you were given in class something with a lot of letters on it that really didn't make any sense. And I'm going to make sense out of that for you. So this is going to be the remainder of chapter 5 that we're going to go over. 5.3, 5.5, and 5.6 all have these triangle congruence theorems. And you can see where they all come from. In your textbook, there's always, in the beginning of every chapter, there's a nice little summary. So 5.3 has the SAS, triangle congruence theorem. 5.5 has the SSS. 5.6 has the ASA and the AAS. And there's one more here, and I'll tell you where that is from when we get to it. So what you're going to want to do is take that foldable that I gave you, and we are going to fold it hot dog style. So it should look like that. And then we are going to cut, now be careful, don't cut the back. Okay, you're just going to cut the front on the lines. This will be like a little flip thing, so you can flip that up and you'll have some information here. Do the same thing for the next one. I'm just cutting right on those vertical lines, but not the back, because we're going to write a whole bunch of information right here. Okay, so there it is. I can flip these up and look underneath them. And we're going to write on the bottom there. Now, how are we going to do this? Well, I gave some directions. So we're going to put the full name. So, for example, SSS actually stands for side, side, side. So I think I'll put that right here. I'll also give you the section, because I would encourage you to go back and study and read through the section, right? Read through what side, side, side actually means. I'll tell you what it is, but it's also good for you to read. We're going to give a description or a definition of the theorem. And then we're also going to do an image of two triangles representing the theorem, including a congruence statement. So triangle blah, blah, blah is congruent to triangle blah, blah, blah. I think we'll start with the image, and then that way I can reference the image as we do the definition. Okay, so for this one, I'm going to do the images up top and then the definition down below. So we'll do two triangles, triangle ABC and triangle DEF. I'll put them in different orientations. So for side, 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 what we're basically saying is that all sides are congruent. Okay, so Side AB will be congruent to side DE. Side CB will be congruent to side EF. And side AC will be congruent to side DEF, or side GF. So therefore, my triangle congruency statement would be triangle CBA congruent to, okay, so I started here, C, and then I went to B. So I'd have to start with the congruent side, or congruent angle, really. And if you look at this, side CB is congruent to side EF. F is going to be the corresponding angle to C. So I'll start with F. Then I'll go over to E, just like I did CBA. I'll go F, E, and then to D, where ED is the corresponding side to BA. So what this is basically saying, let me zoom in a little bit more, is that when I know that all three sides of one triangle are congruent to all three sides of another triangle, then I know that the two triangles are congruent. So if three sides of one triangle are congruent to three sides of another triangle, then the two triangles are congruent. And that was the description or the definition. All right, I'm going to close that one up. We're going to move over to SAS. So SAS means side, angle, side. And that comes from section 5.3. Okay, and I'm going to open that flap up. I'm going to draw my picture up here at the top. So triangle ABC. And triangle DEF. The picture is not perfect. Okay, and this time what we're going to be given is that side AB is congruent to side DE, and side DF and side CA are also going to be congruent, and then the angle between these two sides. So angle D is the angle that touches both side DE and side DF. Angle A is that corresponding angle. It touches both side AB and side AC. So we have that angle that's in between them. So we have a side, an angle, and a side of one triangle congruent to a side, an angle, and a side of the other triangle. And those are all corresponding sides and corresponding angles. So we call this the included angle. This is included because it's touching both of the sides that are congruent. Okay, so that's kind of key there. All right, and so we can write a triangle congruent statement. Triangle ABC will be congruent to triangle, well, let's see, side or angle A goes with angle D. Then I went A to B, so I should go along the corresponding side, so D to E, so it'll be DEF. So that all corresponding angles are in the same position there. All right, so the description or the definition, if two sides and the included angle and that's what I've highlighted up here, is that included angle. That's kind of the key to this one, so I'm going to go ahead and highlight it. Of one triangle are congruent to two sides and the included angle. Oops. Of another triangle then the two triangles are congruent. Okay, so I know that a side, an included angle, and a side of this triangle is congruent to a corresponding side, corresponding included angle, corresponding side of another triangle. Therefore, the two triangles are congruent. Okay, I'm going to skip hypotenuse leg for 1 second. Come back to that one. That's the HL. Oops, I got it right on here. I forgot. So, ASA stands for, hopefully you guessed it, angle side angle. And this one comes from section 5.6. Start with the picture. So we're going to draw our two same exact triangles, triangle ABC and triangle DEF. Okay, so this time you're given an angle that's congruent to a corresponding angle in the other triangle. You've got another angle. How about angle F congruent to angle C? So those two are corresponding. And then you've got the side in between them. So like an included side. Okay, so this is like an included side. It's in between. It's touching both of the congruent angles, both pairs of the congruent angles. So here I can then say, well, triangle ABC is congruent to triangle, well, let's see. A is corresponding to D. Okay, A is corresponding to D. And then B then, well, see how B is not congruent to anything else, so B and E go together. And then C is corresponding to F. Oops, I did the wrong one, F. So that would be our congruency statement. Okay, and so the description of this is that if you have two angles and the included side of one triangle congruent to two angles and the included side of another triangle, then you know that they're congruent. If two angles and the included side I'm going to highlight that because that's what I have highlighted in my images above of one triangle are congruent to two angles and the included side of another triangle. Then the two triangles are congruent. Okay, we're moving on to AAS. What do you think that means? Yep, you guessed it. Angle, angle, side. Oops. Boy. I can spell. Angle, angle, side. And this is also going to come from 5.6. Okay, we'll draw our image, or images. So we'll do triangle ABC and triangle DEF. We'll pretend like those look somewhat congruent. So ABC. Okay, so this will be if I have two angles and a non-included side. So two angles and an, oops. Non-included side. So let's see. So then angle C will be congruent to angle F. And angle D will be congruent to angle A. And then so we'll have triangle ABC congruent to triangle, well, let's see, angle A is congruent to angle D. Angle B and angle E don't have anything, so those are congruent to each other. And then F and C both have two arcs. So there's my congruency statement. and the description or the definition. If two angles and a non-included side. Okay, what do I mean by a non-included side? So see how these two angles are congruent? The side in between them would be included, right? The side not in between them is not included in between those. So those are non-included sides. So I can highlight that too. So these non-included sides, that's what a non-included side is. Of one triangle are congruent to two angles and a non-included side of another triangle. Then the two triangles are congruent. Okay, we got one more, and that's the HL. Now this one is a special one because it's for right triangles only. If you don't have a right triangle, don't even look at HL. And HL basically stands for hypotenuse leg. And it comes from section 5.5. So this time I'm going to have two right triangles. They have to be right triangles. Okay, so two right triangles. Okay, so this basically says that if I have two right triangles and their hypotenuse and their legs, so their hypotenuse and one of the corresponding legs is congruent, then we have congruent triangles. So hypotenuse is always the angle or the side that's across from the right angle. So those ones would be congruent. And then any of the legs, it doesn't matter which leg, it just has to be the same corresponding leg. So maybe we'll do AC and DF. Then I know that these two triangles are congruent. So I know that triangle ACB is congruent to triangle, let's see, so A would have to be corresponding to D, right? Because F and C are going to be congruent. And then E would have to be corresponding to B. Okay, so we'll go D, F, E. Okay, so this says if the hypotenuse and a leg of a right triangle are congruent to the hypotenuse, I'm going to use HYP as an abbreviation, and leg of a second triangle, or right triangle I should say, then the two triangles are congruent. Okay. We're going to apply all of these in class. We're going to do lots and lots and lots of practice. You're going to get a handout in class. But let's go back and let's finish our last example using one or maybe two of these. Okay. So back to our last example, which was example 4. So explain how to prove that triangle PQT is congruent to triangle SRT. Okay, and PQT was my pink one. SRT was my yellow one. And we already said that we knew that in this bigger triangle, PTS, Well, okay, we were given that these two legs or these two sides are congruent. So we knew that this bigger triangle, PTS, was an isosceles triangle. So we were then able to say, okay, isosceles triangle, base angles are congruent. So angle P is congruent to angle S. Now, using one of these, we can see that in each of these triangles, I have a side, an angle, and a side, congruent to a side, an angle, and a side. And the angle is included in the two sides, right? It touches both of the sides that are congruent, right? Touches both of those, like with the 2 tick marks and the 1 tick mark. Touches them. Okay, so that's the included angle being congruent. So that is an example of side, angle, side. So what I now know is that these entire two triangles are congruent. Okay, so I know that those entire two triangles are congruent, therefore, and that's by side, angle, side. Okay, so explain how to prove that triangle PQT is congruent to triangle SRT. I'm going to start with the fact that we know that triangle PST is isosceles. So base angles are congruent. And that makes, let's see, angle P congruent to angle S. Okay, next, we now know that triangle, let's see, I'll go PTQ is congruent to triangle, let's see, let's go STR, trying to put the corresponding angles in the same position. And this is by side, angle, side. Right? Because we have two sides and the included angle congruent to two sides and the included angle. Okay, so that's how we would prove it. Okay, we were already given a bunch of information there. Now explain why triangle QRT is isosceles. So I'll do that one down here. All right, well, now, if you have two congruent triangles, which my pink one and my yellow one are, then that means that any corresponding parts are going to be congruent, right? So we know that QT is going to be congruent to segment RT because these two triangles were congruent. Okay, so I can say something like, since triangle PQT is congruent to triangle SRT, all corresponding parts are congruent. So we can then say segment QT is congruent to segment RT. And now because two sides are congruent in this triangle QRT, then we know that it's an isosceles. We'll say something like triangle QRT is isosceles because two sides are congruent. So that's just an example of how you start using these. And like I said, tomorrow in class we'll use all of these. We'll do a bunch of problems together.